This is part 1 of the 4.3 section on exponential functions. An exponential function is a function that has the variable in the exponents. So you'll see on this example, the variable is in the exponent, the variable being x. A is the base, A is a value that is greater than 0 but not 1, and C is the leading coefficient, which is not equal to 0. The value of A is called the growth factor, whereas the value of C is called the initial value. When the function begins, when x is equal to 0, let's say that represents a time variable, it would make sense to have a function to represent the growth or decay of a quantity over a period of time. And so therefore, when the time begins, when x is equal to 0 or time is 0, the value of C is your initial population or the initial quantity that you have to work with. When you're working with an exponential function, the ratio of consecutive outputs is constant, which means if you have a table of values, let's skip down to this example. If you have a table of values, notice that in the first column, the values of x increase by 1 as you go down the table from one line to the next. And the value of g, which is your output, is going to change by a certain amount. So if that certain amount that g is changing by is a continuous or a constant ratio, then we can say that your table represents an exponential function. So let's look at example 26. In example 26, like I said, the x values go up by 1 unit each time, and the output values go up by the same quantity, which is 3. So from 2 to 5 is a difference of 3. This is 3. From 5 to 8, the difference is 3. From 8 to 11, it goes up by 3, and from 11 to 14. So this is not going to be representing an exponential function. This is not exponential. Because to be exponential, your ratio, which is going to be found by a common factor, would need to be constant. This one is going to give us a common difference. The difference is common, and that common difference in example 26 is what that value 3 represents. 3 is the common difference. In this case, in example 26, this table of input and output values represents a linear function. And furthermore, the slope is 3 over 1. Remember, this is the change in the output values over the change in the input values. And that is equal to this common difference, which we identified to be 3. In example 28, we're going to determine if this table represents an exponential, a linear function, or possibly neither. So you want to look to see how the values of x are increasing as you go down. Same thing as example 26. These are going up by 1 each time. The output values, this time f of x, is not increasing by the same amount. That is, you're not adding the same amount to go from one value to the next. All right, so the first example, we kept adding 3 each time. We're adding 3. That's a common difference. Difference is 3 between each of those output values. In this example, it's not going to be adding or subtracting a common amount, but instead multiplying. So how would you go from 3 halves to 3? What value would you multiply 3 halves by to get 3? 3 halves times how much would give you 3? And so you might play with the numbers a little bit and find out that the common factor is going to be 2 times 2. So to go from 3 halves to 3, you multiply by 2. To go from 3 to 6, you multiply by 2. To go from 6 to 12, you multiply by 2. From 12 to 24, we multiply by 2. And so in this situation, we have 2 represents the common ratio. Okay, so I'm not increasing by the same amount by adding the same quantity. Instead, I am going to be multiplying by the same quantity to get from one output value to the very next consecutive output value. For that reason, this relationship is a exponential. All right, so now we're going to go back up to the part that I jumped over here in the middle to determine how do you know if you have an exponential function. It says that the ratio of consecutive outputs is constant. And so this case, you were looking at one output value divided by, that's what makes a ratio, divided by the preceding output value. And if you get the same number each time, which we're calling A, then what you have is an exponential relationship or exponential function. So that is what we have in example 28. We have a common ratio that we found to be 2, right? Multiplying by 2 each time. And so my value of A would be 2 in that case, right? So what we're doing now with this line is we are simplifying it or just rearranging the pieces, and that is going to get you to what you see right below, all right? So those are equivalent statements. Now let's discuss the graphs of an exponential function. It looks like my function notation got chopped off here. How about we call this f of x? F of x is equal to c a to the x. So in this case, we're going to let c, your initial coefficient, we're going to let that be positive. The value of a is something that's bigger than 1. So if you want to make up some numbers to make a little bit more sense out of this general example, that might help you. Let's say f of x equals something like 2 times 5 to the x power, right? Exponential functions have the exponent as the variable, which is x. In this case, the pattern that you're going to notice is going to be the same. Whenever the value of c is bigger than 0, it's positive, and this base is bigger than 1, the pattern is going to look the same in the graph. The graph shape is going to look the same. And essentially, the graph shape is going to start out slow, and it's going to increase like this. That would be a general graph of an exponential function with that set of criteria. The domain is all real numbers, and the range is anything that is positive, that because it stays above the x-axis. Graph is above. In the next example, in general, we're going to assume that, let's make this f of x once again. Our function has a leading coefficient. This time is negative, but the base is still something bigger than 1. So to make sense out of this, you might consider a function like, how about negative 2 times 5 to the x. So what effect does that negative sign have on your function from above? Well, it's going to represent a reflection, right? From what we learned about function transformations way back in chapter 1, we know that whenever we put a negative sign into our function, it is going to be a reflection. So the question is how does this reflect? Does it reflect across the x-axis or does it reflect across the y-axis? And the answer is that this needs to reflect across the x-axis. So the graph from above is going to look something more like that. In this case, the domain is all real numbers. Once again, we are allowed to use anything we want to for x, but the range this time stays below the x-axis. Graph is below the whole time. No matter what the value of x is, the graph stays below the x-axis. The next general example is going to be a function. This time we're going to make the leading coefficient positive again, but look what happens to our base. It's a number between 0 and 1, such as maybe 1/2 or 1/5 or something like that. So to make sense out of this, consider with the graph, let's go 2 times, and then we're going to do 1/5 to the x power. What effect is this going to have on your function? Okay, so the effect that this is going to have is it is going to decrease quickly and then level off. And it's going to have that general shape. Domain is anything, the y values are all greater than 0. And finally, this last example, once again, your base is a fraction between 0 and 1. This time your leading coefficient is a negative number. So we can take the graph that you see directly above and reflect that across the x-axis, and it's going to look something like this. That's the general shape. So become familiar with these general shapes of exponential functions to understand how you would get graphs if you would translate them in various ways. We're going to use transformations of the graph that we just talked about, the graphs we just talked about in general, to figure out what this particular function is going to look like. We have to identify the domain, the range, horizontal asymptote for each function. So this function, f of x equals 3 to the x minus 1, has a base equal to 3. The base is 3. All right, that is definitely a number that is bigger than 1. So when you look at your notes from above, we are going to consider the graph where the base was bigger than 1. The leading coefficient could be considered a positive 1. There's nothing there. It's positive, though. Therefore, the general shape that I'm considering right now was the one that went like this, the very first graph. So on the graph of, let's just consider what 3 to the x looks like. This could be 3 to the x, right? No transformations. The base 3 is bigger than 1. The leading coefficient is positive. Identify a point. And the most convenient point on that basic graph is going to be that y-intercept. This is obtained by letting the x-coordinate be 0. If the x-coordinate is equal to 0, that means that the output value is 1. So this contains the point 0, 1. So when you transform this graph for 43, we want to figure out where the point 0, 1 goes to. So the understanding that we acquired back in chapter 1, when we subtract 1 from the input location, here the input is in the exponent. When we subtract 1 from the input, that is a horizontal shift. We want to horizontally shift. Because I'm subtracting 1 from the input, I want to shift to the right. 1 space. So that's going to take the point 0, 1 and it's going to move it to the point 1, 1. So locate that on your grid. There's the point 1, 1. Everything else shifts to the right as well. The original graph of y equals 3 to the x has a horizontal asymptote, which is the x-axis. In other words, it's the line y equals 0. Okay, so the line y equals 0 is your horizontal asymptote. That does not move. That stays in the same place because if I shift that horizontal line to the right 1, it looks the same. So I'm going to go ahead and sketch in my graph just on that limited information. This is what we get. The domain of every exponential function is all real numbers. Anything is allowed to be used for x. The range is going to be what types of output values are you getting. In this case, we are strictly above the x-axis, so all my y's are positive. And the horizontal asymptote, as I mentioned, did not change from the basic graph. It's still the x-axis, or the equation y equals 0. The next example, number 50, gives you a function where there's a few different transformations going on. The adding of 1 is a vertical shift. That's going to go up 1. The plus 3 that's here in the exponent, that's horizontal. It's going to go left this time because it's a plus 3. We go left. And then this negative sign is a reflection. And we learned earlier, just a few minutes ago, this means reflect across the x-axis. Had that negative sign been up in the exponent along with the x, it would be a reflection across the y-axis. Okay, so where does that original 0, 1 point fall, right? 0, 1 is always the point on your basic exponential graph. No matter what your exponential function is in its basic form, the point 0, 1 will always be on the starting graph. That's without any transformations. So the first thing we want to do is we can reflect it across the x-axis. And so if I take the point 0, 1 and reflect, across the x-axis, where does that point go? It's going to go to 0, -1. The next transformation I will apply is going to the left. Go left 3, okay? Go left 3. So where does that new point, 0, -1 go? It's going to go to -3, -1. And then the last transformation is to go up 1. Up 1. So now the point -3, -1 goes to -3, 0. So this is my crucial or my key point. That is my key point. Okay. What about the asymptote? So the original horizontal asymptote, which was the equation y equals 0, right? It always starts with the x-axis as your horizontal asymptote. As you reflect across the horizontal axis, or sorry, the x-axis, that does not go anywhere. Reflection on itself doesn't change. When you go to the left 3, that does not change. But when you go up 1, now it moves up along with it. So the equation y equals 1 is your new horizontal asymptote. And your function needs to stay below. Remember how there was that reflection that flipped it downward? Okay, so we're going to move that downward, stay underneath the horizontal asymptote, and it's going to go something like this. Your domain is all real numbers. Your range is all y values that stay below 1, and your horizontal asymptote is that line y equals 1. 56, e to the x. Now, e is an irrational number. Its approximate value, e to the first, is approximately 2.718, and it goes on forever. It's similar to the idea of pi. You know about pi. So e is another irrational number. It's used quite a bit in the science fields. Finance uses this irrational number e as well. You'll see this pop up in different future classes. Maybe you've already seen it. So that's just a base. It's a number. It's approximately 2.7. We are going to consider what the general graph, y equals e to the x, might look like, and then build our transformed graph for 56 off of that. So the basic graph of y equals e to the x looks just like you might have expected. The base is bigger than 1, so it needs to be increasing. It contains this key 0.01, just like all basic exponential graphs contain. And so we are going to take that concept and apply transformations to get this new graph for 56. The only transformation I'm concerned with is that -1. That's a vertical shift. I'm going to go down 1 space. So the 0.01 goes to 0, 0. All right, let's talk about the horizontal asymptote. Initially, the horizontal asymptote is your x-axis, so that's the line y equals 0. If I shift down, does that move the horizontal asymptote? And the answer is yes. Move that down. And now it becomes the line y equals -1. So your function did not do any reflecting across that horizontal axis. It stays above, so it's going to have this basic shape with that new horizontal asymptote. So the domain, all real numbers, the range, all y values that are bigger than -1 this time, and the horizontal asymptote is the line y equals -1.